Solving trig equations with u-substitution. So remember the first step in our solving process. We have to get the equation to look like this. A single trig function, a single variable, an equal sign, and a number. Well, what are we going to do if the item we have in here is not just a single variable? That's where u-substitution comes into play. Let me show you how it works. I've got a couple of simple steps I can take here, subtracting 1 from each side, and then dividing both sides by 2 to get rid of that front coefficient of 2. And I'm very close now to that format that I want. I just have that 2x sitting here, and I can't get at this 2. It's trapped inside the sine function. Well, the solution here is to make a u-substitution. What I do is I decide to call that inner thing u. So I'm going to say that u is equal to that 2x. That allows me then to write this in the correct format. Trig function, single variable, an equal sign, and a number. At the very end of the problem, we'll go back to x, but for now, we'll do our normal solving process with this equation. Sine u equals -1/2. I can move on to step B now, finding all the solutions within one period. Let's see, all students take calculus. Sine is positive in the first two quadrants. Sine is negative in quadrants 3 and 4. So I'll be drawing a reference triangle picture here and a similar symmetric reference triangle in quadrant 4. Let's see, sine is opposite over hypotenuse. And I'm supposed to recognize this as a special triangle. It has to be a special triangle. We're giving exact answers. It is, of course, the 30, 60, 90 triangle. And the reference angles in both cases are 30 degrees. 30 degrees opposite the 1. Well, I'm interested in this third quadrant angle and then this fourth quadrant angle. Let's see, the smaller one would be 30 degrees past 180, 210. I'm supposed to work in radians. 210 would be 7 pi over 6. And then the larger angle is 30 degrees short of 360. That would be 330, which in radians is 11 pi over 6. So there's step B, my two solutions within one period. Now, we want all the solutions, so I will go ahead and move into step C. And we know that's pretty easy. I just take each solution and add on a multiple of the period, a multiple of 2 pi. But this is the point where I have to remember that u was something I made up. There was no u in this problem. I want to solve this equation for x. And so at this moment, I will take my answers for u and I will substitute back for x. In other words, I will replace u now with 2x. I'll do it in that first version and I'll do it in that second version. So I have 2x equals 7 pi over 6 plus 2k pi, and 2x equals 11 pi over 6 plus 2k pi. And then I just need to solve each of these equations for x. It's pretty simple here. I just need to divide both sides by 2, although I'm looking at the fractions and thinking to myself, maybe if I multiply each side by 1/2, which is the same thing as dividing by 2, that might be easier to write down. So let's multiply in both cases the left and right sides by 1/2. And what I get will be my final answers. This became just x, that's great. 7 pi over 6 times 1/2 would be 7 pi over 12. And of course, when I cut 2k pi in half, the 2's will cancel, leaving me with just multiples of pi. Similarly, in the second set, I'll end up with 11 pi over 12 plus those multiples of pi. Here are the final solutions to the equation. Now here's a follow-up question. What if I didn't want all the solutions? What if I just wanted the solutions within 0 to 2 pi? You say, well, didn't we find those already? The 7 pi over 6 and 11 pi over 6? No. Those were u values. I want all the x values within 0 to 2 pi. This is why it's so important that you don't go back to x until after you've done the multiples of the period thing. It's only once you've gotten to this step that you can answer a question like this when you're dealing with u-substitution. In the past, we would skip step C for these sorts of problems, but with u-substitution, you must take it all the way through step C. Don't substitute back until the very, very end, and then if you want some of the answers, you can find them easily from your final statements here. Let's write them down. Obviously, 7 pi over 12 is between 0 and 2 pi. And then I can add on any multiple of the period. Well, let's add on 1 pi. That would be adding on 12 pi over 12. So that would give me 19 pi over 12. 19 pi over 12 is still allowed. I can basically go up to 24 pi over 12, right? That would be 2 pi. So can I add another multiple of pi here? That would be another 12 pi over 12. No, that would get too big. That would take me to 31 pi over 12. That's over 2 pi. So I've exhausted the answers from the first line. How about from the second line? Well, definitely 11 pi over 12. Can I add a pi to it? That's 12 pi over 12. That would bring me to 23 pi over 12. That's still good. That's barely good, right? 24 pi over 12 is the limit. Obviously, if I added another 12 pi over 12, I'll be way over. So by adding multiples of pi, 12 pi over 12, we were able to find all the solutions. Note that we really would not have been able to find these things unless we had gone all the way to the end. Thanks for watching.